In this video, we will try to visualize the ligand group orbitals using a real example. We will take an octahedral molecule and try to decode the molecular interactions. Let us use the classic octahedral complex, hexamminocobalt 3-chloride. Here, the octahedral symmetry is clean, NH3 is mainly a sigma donor and the LGO picture becomes very clear. Now, try to visualize the actual molecule. We have a cobalt at the center and 6 NH3 ligands approaching the metal along the X, Y, and Z axis. As the complex is octahedral, it is the best possible way the ligand can approach the metal to minimize the energy. You can think, why the ligands are not approaching the metal along the direction of metal orbitals. It is tempting to think, ligands should approach metal, where metal d orbitals point. However, this is not generally true. Because the metal has many orbitals, and if ligands come in all directions, where the metal orbitals are pointed, they will repel each other. Therefore, the organization must support the whole molecule to minimize total energy. So, the ligands orient themselves along the axis. Now, we have 6 NH3 ligands, each having a lone pair and pointing towards the metal along the Cartesian axis. We will represent these as Lx plus, Lx minus, Ly plus, Ly minus, Lz plus, and Lz minus. But we know the orbital not a physical object. It is a wave. In an octahedral complex, the ligands are physically arranged around the metal with approximately equal bond lengths. This is the actual molecular geometry. This part is physically real. Once the ligands approach the metal closely enough to form a bond, the electrons are no longer purely localized, the wave functions overlap, and the electronic states become coupled. In molecular orbital language, ligands no longer remain electronically independent. So what actually interacts? It is the electron wave functions that interact. Since these are waves, interaction is a natural process. The ligand donor orbitals overlap with the metal s, p, and d orbitals. And because all ligands simultaneously surround the metal, their combined wave functions interact with the metal orbitals. An individual ligand does not interact with the metal independently. But how they will interact will be decided by how they are arranged. That is why group theory is so important in molecular orbital theory. Because, from group theory, we can get the molecular symmetry, and it helps us to group the metal orbitals as per their symmetry and assign irreducible representation. And since the ligand arrangement is restricted, and if we consider their combination as a basis, we can assign the irreducible representation to them. When the symmetry of ligand group combination matches with the metal orbital symmetry, effective overlap takes place and lead to formation of strong bonding orbitals. This naturally produces collective interaction patterns and symmetry-adapted combinations, which we call LGOs. Their electronic wave functions become part of one delocalized molecular electronic structure. In our example, the molecule belongs to octahedral symmetry. So by using the octahedral point group character table, we can assign the irreducible representation to the metal d orbitals. Since the s orbital behaves like x square plus y square plus z square, it transforms as A1G under octahedral symmetry. Similarly, dx square minus y square and dz square transform like, e.g., dxy, dyz, and dzx transform like t2g, and px, py, and pz transform like t1u. Now we will try to assign the irreducible representations to the different combination of ligand orbitals. Here first we will define the basis. Here the basis is 6 ligand orbitals. However, before we start, there is one important disclaimer: we do not assign irreducible representations to all possible combinations. Since we have 6 ligands, we can generate hundreds of different combinations. We do not have to consider all of them. Instead, we start with the 6 ligand orbitals as a basis, determine how this basis behaves under the symmetry operations of octahedral point group to obtain a reducible representation, and then decompose it into irreducible representations. For an octahedral ML complex with sigma-donor ligands, we will have Lx plus, Lx minus, Ly plus, Ly minus, Lz plus, and Lz minus. These 6 ligand orbitals are our basis functions. Now, we will find the reducible representations for the 6 orbitals under the octahedral symmetry operations. For that we shall see how these orbitals behave under symmetry operations. For example, under E all orbitals remains the same, so the character under E is 6. Under C4 rotation about Z, except Lz plus and Lz minus, all other ligands change their position, so the character of Lz plus is 1, for Lz minus, it is also 1, and for all other, it is 0. So, the character under C4 is 2. Similarly, we can determine the reducible character for all other operations, and we will obtain the reducible representation as tau sigma for the 6 sigma-donating ligand orbitals. Next, when we reduce the reducible representation using the reduction formula, we will get A1G plus T1U plus EG. It means the entire 6-dimensional ligand space can be rewritten as 1 orbital of A1G symmetry, 3 orbitals of T1U symmetry, 2 orbitals of EG symmetry. Now, we can construct the actual ligand groups. Here, we are not randomly inventing any combinations. We are asking, can the ligand combination produce a wave pattern that looks like a metal orbital? Because only then can strong overlap occur. For A1G, which is totally symmetric, LGO must be Lx plus, Lx minus, Ly plus, Ly minus, Lz plus, Lz minus. For 3T1U symmetry, since X, Y, and Z transform as T1U, we have T1U, kiss smiley is equal to Lx plus minus Lx minus. T1U, Y, is equal to Ly plus minus Ly minus. T1U, Z, is equal to Lz plus minus Lz minus. These 3 combinations are valid because they match the metal, Px, Py, and Pz symmetry respectively. For EG symmetry, we have EG 1 such as and EG 2 such as that match with dx square minus y square and dz square, respectively. But we do not have any T to G type ligand orbitals in the octahedral arrangement. So, the A1G type LGOs overlap with the s orbital. T1U type LGOs overlap with the p orbitals. And EG type LGOs overlap with dx square minus y square and dz square orbitals. Since there is no T to G type LGOs, the T to G metal orbitals do not get a chance overlap with any LGOs and remain as non-bonding because of the symmetry restrictions.